Hi class, welcome to chapter 1.9, the coordinate plane, graphs of equations, and circles. So this is where we're going to start talking about graphing, basically. Looking at equations as they pertain to their graphs, and just all the different aspects of graphing. So graphing is very, very important. As we move through calculus, your ability to understand equations, functions, and their graphs is going to be very, very, very important. In calculus, we really analyze functions and their graphs like a lot. So this is going to be our introduction into the coordinate plane and the coordinate system. There's several ways of looking at a single coordinate. I'm going to really just focus on the basics today, the Cartesian coordinate system, the rectangular coordinate system. But in this class, we will talk about polar coordinates and things like that, change of bases, rotation of axes. They all come up later on in this video, or not this video, but this video series. In Calculus 1, we really analyze the graphs of functions and how it pertains to calculus. Okay, so it's a very important skill to have, to be able to visualize the functions that you're analyzing. Okay, especially once you get into Calculus 3, you move into the three-dimensional world, and everything, all the functions you talk about are three-dimensional functions. They're no longer just up, down, left, and right. You also have that in and out sort of addition to the two-dimensional system. So very important that you're familiar with the graphs of your functions and the way that we read a function and its graph. Okay, so we're not really focused on functions yet, but we are focused on equations, right? So we're going to look at graphs as equations and circles. A lot of times circles are overlooked in the algebra course, so we're going to introduce them here. I'm going to assume that you probably haven't done a lot of math with circles. Depending on who's looking at this video series, maybe you are very familiar with circles and their equations. So let's start off with the Cartesian coordinate system. Okay, this is our standard rectangular coordinate system that we use for graphing. Okay, there are other coordinate systems, which again we will talk about in this class, but for right now we're going to focus on the most common, which is the rectangular coordinate system. Okay, so the way that we describe a point in the Cartesian coordinate system is by using an ordered pair. Okay, an ordered pair. So that means that we are going to be given a pair of numbers, two numbers. Okay, one of them relates to what we call the value of x, and the other is our value of y. Okay, x is the value away from 0 along the x-axis. The x-axis is a left to right axis. Okay, so it's the distance from the origin. Okay, the origin is given by the point 0, 0 in an xy Cartesian coordinate system, right? Y represents the distance up and down from 0 or from the origin, okay, along the y-axis. And the y-axis, again, is that up and down axis. So here, x translates to the left and right. Y is the same as up and down. So xy is the same as my left and my left and right from 0. And then the y is the up and down from my 0, okay? So if this is my coordinate system grid, this is 0, 0, okay? If I move over, so here, very important, okay? When you guys draw your coordinate systems, you have to label everything, okay? So this is x, this is y. I have no idea what these numbers are, right? It's not scaled. I know you're probably saying, oh, well, it's 1, it's 2, and it's 3. But maybe it's not. Maybe we're counting by 5s. Maybe we're counting by 3s. Maybe we're counting by hundreds. I have no idea here. There's no scale, okay? So when you draw a graph for me in my class, always scale your axes, okay? And you have to scale them evenly. You can't say that this is 1, 2, and 12, right? It has to go 1, 2, 3, 4, 5, however. You can count by 2s, you can count by 1/2, you can count by whatever you want, as long as it's spaced out evenly, okay? Now, if this is my point in the universe that I live in, which is a two-dimensional system, right? Up, down, left, right. This point here can be talked about, right? It can be specified to a reader by saying, hey, it has a value of x, y. So what that means is that from the center, you move over a distance and up a distance and the distance you move over left and right is a distance of x. Okay, again, there's no scale here, so you can't say, oh, that's 2 and this is 3. You have no idea what these numbers are, right? It's a distance of x. And the value up that you go is a distance of y. So any point in the system is over x and up y, right? If it was a point here, I would go over x, up y. If it was somewhere down here, over x, down y. Okay, so any point has a left and right distance from the center of x and an up and down distance from the center of y. So you go over and you go up. A lot of times it's similar to talking about city blocks. If this is where you are and this is where your friend lives, okay, and each of these are neighborhoods, city blocks, like a downtown type area, you would go over 1, 2 of these blocks and then up 3 of these blocks, right? So it tells you have to go over this distance, this many blocks, and then you go up this many blocks to reach your friend's house, okay? So we can use set builder notation to describe regions of the graph, right? So here, a point to me describes a single point on the graph. So let's say I want to describe an entire area of the graph, right? So example, let's say I'm interested in the region described by all the points x, y, such that my x's are all larger than 2 and all of my y's are less than or equal to -3. Okay? So I have my coordinate grid, my rectangular coordinate system, my Cartesian coordinate system. As you can see, my axes are numbered. Okay, my x and my y axes are numbered, so now I can actually do some math and it'll have some actual meaning because these units are not arbitrary, right? So I need my x values to be larger than 2. So along x, right, this is one number line and this is another number line. That's really how you should think about it. It's two separate number lines overlapping at their zeros, right? So on the x number line, I need to go to 2, okay? And I can draw a line straight up and down, okay? Because now that separates all the values of x that is larger than 2 versus all the values of x that is less than 2. And if you notice, I drew a dashed line because in a two-dimensional system, when we have inequalities, a strict inequality is represented by a dashed line. So I'm not allowed to be 2, okay? That's why it's dashed. And it's now separating the things that are x values larger than 2 and the x values that are less than 2. Okay. My next line of interest is y equals -3. So if I go down along my y-axis, this line separates all the y values, all the things above -3, so all the y's that are larger than -3, and all the things that are below -3. I have a solid line because I'm allowed to have the value of -3 in this set. Okay, so now I'm looking for the overlap of the things that are larger than 2 in the x world and less than 3 in the y world and also equal to 3. And I can shade that in. So a lot of times when you learn this in Algebra 1 or Algebra 2, you shade both the areas and then you're just looking for the overlapping shaded area. But again, this is review, so you should be able to just draw these lines and say, this is my piece of interest at this point, right? So that's the way that this works, okay? So now let's talk about distance. Okay, you've probably seen distance before, but again, we're going to go a little bit deeper, talk about this with some notation that we're used to, right? The distance between any two points in two dimensions, okay? My first point I'll call P naught. It's signified by X naught and Y naught. I know you say, well, that's a 0. Generally, we call it naught when we have a subscript of 0. Naught just means my initial point, okay? So this is my initial point. This is my second point, P1. So that's given by a point X1 and Y1, okay? The distance between these two things is notated as the distance between P0 and P1, okay? And it's calculated with the Pythagorean theorem because the distance between any two lines, 2 points, is a straight line. And from that straight line, we can draw a triangle, okay? So we're going to use the fact that a squared plus b squared equals c squared, where c squared is the longest side, okay? A triangle will be formed from these 2 points where one of those legs, which we'll call A, right, which we're interested in squaring, is going to be parallel to the y-axis. So again, parallel means train tracks, right? Runs alongside of it. And the a value can be signified with the absolute value of y1 minus y0. So remember, when we're talking about distance, we're using absolute values before. Okay? So a is a length. Its length is y1 minus y0 or y0. If this happens to be negative, we take the absolute value so that it's positive because length has to be positive. Okay? The other leg, which we call b, is parallel to the x-axis, right? So it runs left to right. And it's going to have a length very similar to the first, okay? It is going to be the absolute value of x1 minus x0. Okay? The distance between the 2 points then follows as such. The distance squared, my c squared, right, my distance, is going to be my a squared plus my b squared. I think I flipped these around, so this is really b squared plus a squared. It's the same thing, doesn't matter, okay? And remember, absolute value is always positive, but so are squares, okay? If I take a negative number and I square it, I'll get a positive number out. So I can actually drop this absolute value sign because whether it's a positive value in here and I square it and get a positive, or if it's a negative value in here, right? If this absolute value was not here, I would still square it and still get a positive, right? So absolute values in squares, they're always both positive. So I can drop the absolute value sign and I can make it a little bit easier to read by writing it like this. Okay. Now remember, I'm interested in the distance. I'm interested in this value c. So if I want to get distance, but I have distance squared, well, that means I got to take the square root of both sides. Okay. Now remember, distance is always positive. So I don't have to worry about the plus or minus form here. I only have to worry about the positive answer when I square root this because again, distance is always positive. So the distance between P0 to P1 is the square root of the sum of the squares of the differences of their x values and their y values. Okay. So let's go ahead and look at this with the graphical representation because again, I'm sure this made some sense, but maybe not 100%. So let's look at what this looks like. So we have a point, which we call P0. Its position is given by some x value and some y value. We have some other point anywhere in space. So again, we're staying in the first quadrant in our coordinate system. However, it could be anywhere, okay? That's why these are general values. So my second point is P1. It has a position given by x1, y1. And the distance between them is a straight line. Okay, I just connect those with a straight line. If I went from this point to this point along the horizontal, okay, parallel to the x-axis, right? So again, let's say that this was a city. If I wanted to get from here to here, I can't go through buildings, okay? I would have to go down the street a few blocks and then go up the street a few blocks in order to get to my new point. I'm not Spider-Man or Superman. I can't jump from here to here, okay? There would be objects in my way. So that's the distance between the two. But in order to get there, I would kind of have to go in a roundabout way. So think about it that way, right? So the distance from here to here, okay, and then from here to here, this has a y value of y0 because this y goes with this point. This y value for this point is y1. Okay, so the distance here up and down vertically is this value minus that value. Okay, and the distance from here to here, from x0 to x1, is the difference between the values, right? So again, if I have a distance of x1, okay, so from 0 to x1, and then I subtract this, this is what I'm left with, right? The value in between x0 and x1. So this value is x1 minus x0. This distance is y1 minus y0. And so if I want to find the length of this, I have the Pythagorean theorem. This squared is equal to this value squared plus this value squared. Okay, so this, from here to here, that's the distance from P0 to P1. Okay, so again, just to reiterate, coming back, okay, This squared is this value squared plus this value squared. Take the square root, and this is what we have. That's why the distance from P0 to P1 is the square root of the sums of the squares of the differences of the x values and the y values. Go through this whole animation one more time. So midpoint, okay? If I want to know the midpoint between here and here, right, the value right in the middle, I can do that. The midpoint between 2 points is the location of the exact center of the line that connects the 2 points. Okay, so this is the line that connects the 2 points. The exact center of this line is the midpoint between them. The distance from the midpoint to either point is equal. Again, the distance from here to here is the same as from here to here. Okay, we say it's equidistant from the endpoints. So the midpoint is the same distance from itself to P1 as it is from itself to P0 or P0, right? So to find this point, we take half the distance between the x0 and the x1 value, and we add that to x0, or we can subtract it from x1. That's one way to think about it. An easier way is that we just average those two x values. The point in the middle is the average of those two values, okay? So we want to verify that all three of these methods are equal. Okay, so as you write this, I'll let you submit to me as extra credit for those of you who are in my class right now. Okay, so verify that these three methods of the midpoint are equal. Okay, so we have a point. Again, that's my P0. I have a second point arbitrarily placed in space. It is P1 given by x1, y1. I connect them with the line. I go along the horizontal. I go along the vertical. I know what those distances are. Halfway between x0 and x1 is the average of those two values. Another way of thinking about that is that I can find the difference between these things. Okay, x1 minus x0. Split it in half, so that'll give me this length, and then I add it to x0. Or I take this length and I subtract it from x1. Either way, that'll give me to the same point. Okay. So if I follow this up along, it'll reach the x value of the midpoint of that line. I do the same thing for my y's. Okay. All right. This gives me the midpoint, which is xm and ym. M for midpoint, so this is the x midpoint value and the y midpoint value. Okay. So as a point, the midpoint looks like this: 1/2 x0 plus x1 and 1/2 y0 plus y1. So again, it's the average of your x values and it's the average of your y values for the 2 points of interest. So for graphs of equations in two variables, right? So when we have two variables, one acts as what we call the dependent variable, and the other is the independent variable. Generally, x is the independent variable and y is the dependent variable, although these can switch roles depending on what we're talking about, right? So for a dependent variable, it's easy in concept to understand what it means, right? So its value depends on the value of the independent variable, right? The independent variable depends on nothing but the situation that you are talking about. For instance, if I'm talking about somebody's speed over time, time is independent. Time continues to move no matter what is happening. Okay, it doesn't stop, it doesn't slow down. Time does its own thing. However, the runner's speed depends on the amount of time they've been running. They'll slow down, they'll speed up. Maybe at this point in time they've reached a hill, so they go slower or faster if they're going downhill. Right? So their speed is dependent on the time as they get tired, etc., etc. So certain things are always independent variable. Time is generally always independent. Anything that depends on time is obviously your dependent variable. Okay? The value of an independent variable does not depend on any other value. Okay? Typically x is independent, typically y is dependent. So we say that the value of y depends on your value of x, right? If x is 5, I plug that into my equation and I will get out a value of y, right? So depending on the x that gets plugged in will tell me what y comes out. Okay. A tedious but foolproof way of graphing an equation in two variables is to choose numerous values for your x variable. Okay. So usually the values you choose for x are centered around the origin. So you'd pick like 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. You'll just choose a bunch of x values. Typically you don't choose halves or 3 halves. It really depends on what your function looks like. To be honest, sometimes choosing a half or 1/3 is better than choosing a value of 2, right? It really depends on if your equation has fractions in it or not. And you just plug those x values into your equation to get out your outputs of y, and then you have your x and y value coordinate pairs, and you just plot those. Okay. Now, that's nice and everything. It always works. It will always work. You can always graph a function. There's no reason for you to ever not be able to graph a function. Now, it could just be a lot of work. Okay. A better way is to understand what a few functions look like and how to manipulate those into the equation that we have present for us, which we talk about in chapter 2. How do we take a regular set of functions and manipulate them so that they look like the function that we have before us, right? So once we have enough points, we always can just connect those points with the line, right? So right now we're going to talk about a little bit easier ways of doing this. Okay, so again, this is probably the worst way to graph an equation, but it's the way that you guys always learn from the beginning on how to graph. They say, hey, plug in this x, plug in this x, plug in this x, get all of these points, plot them on your graph, and connect them with the line. Again, it always works, but it's the worst thing to do. Okay, so it helps us in the beginning to get an idea of what our graphs look like, but at this point, it's pre-calculus. You should have an idea of what most graphs look like in general. So we're going to be learning various ways to graph an equation based on our prior knowledge of algebra already, right? So things like intercepts are going to be very important to us. So intercepts are the points where our graph intercepts the x-axis or the y-axis, okay? So those number lines, wherever our graph crosses those number lines, that's an interception of our line for our graph with those number lines. So those points are called intercepts. Okay. So in order for a graph to lie on the x-axis, there must be no movement in the up and down direction. Okay. So let's go to one of these graphs here. Let's go here. Okay. If I want to be on this number line, okay, if I want to be on the x-axis, here, 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 it doesn't matter where, my distance from 0, left or right, is a distance of x. But my up and down distance from 0 is 0. There's no movement up, there's no movement down. From here, I've only moved left, or I've moved right. I have not moved up or down at all. Similarly, if I want to be on the y-axis, right, notice what I'm doing. I'm going up and down, but I'm not going left or right. So if I want to be on the y-axis, I can only move up and down. I cannot move left or right. If I want to be on this axis, I can't move up or down. If I want to be here, I can't move left or right. Okay. All the way back to our slide that we're on. Okay. So, if I want to be on the x-axis, there must be 0 movement in the up and down direction. So what that means is all of my x-intercepts have the form of a left or right distance from 0 of x, but 0 movement up or down. Okay. Similarly, if I want to be on the y-axis, my y-intercepts have a form with no movement left or right, but I do have up or down movement. Okay, so the easiest way to remember this is that for an x-axis, okay, an x-intercept, the opposite variable of interest to me is 0. So on the x-intercept, I have an x, no y. On the y-intercept, I have a y, but no x. Okay, so x is 0 for a y-intercept, y is 0 for an x-intercept. So y equals 0 means that I have an x-intercept. Okay, here, y is 0. X is 0 means I have a y-intercept. So again, notice the difference here. Y is 0 means I'm on the x-axis. When x is 0, it means I'm on the y-axis. Okay, so we look at this here. All right, so here I have some weird looking graph on here. Okay, so my x-intercepts are all the places where this graph intercepts the x-axis. Okay, so those are all the points where they overlap each other, where they cross each other. Those are my x-intercepts. Okay, all the places where my function crosses my y-axis here is my y-intercept. So those are the difference between the two. Okay. All right, let's talk about circles. Okay, a circle is centered at a point. We call that point H and K. There's an important reason why we use H and K, which we will see in chapter 2. Okay, there's some standardized notations for us. A circle has a center and it has a radius. Okay, on the Cartesian coordinate system, that center, we call it H and K. Obviously, H is an X value, K is a Y value, right? So that's where the center is, and it has a radius of R. That's true, then the equation for a circle is going to be X minus H squared plus Y minus K squared equaling R radius squared, right? And it looks like this. So here, this is a distance of H, this is a distance of K, that's why this is the point HK. If I want to be a point XY anywhere on my circle, okay, that's where the X and Y comes in. If I plug in X and Y into this equation, it should satisfy, when I simplify it down, to equal whatever R squared is, right? So any of these XYs on the outer rim is on my circle will have a distance away from HK of R, okay, because R is the radius. So let's do an example. Find the equation of the circle that has a diameter with endpoints -9/2, 7/2, and 1/2, -3/2. So diameter is twice the radius. Okay, so that means that this is one point and this is the other point. Those are the two endpoints of my diameter. A diameter always goes through the center of a circle. Okay, so the other thing we want to do is we want to find all of the x and y intercepts for the circle. So if this circle, maybe it's off-centered here somewhere, we want to find all the points where it crosses the y-axis and all the points it crosses the x-axis. Okay, we want to find the center and the radius of this circle. So this is our example. I'm giving you 3 points. A and B goes together. C is somewhat different. We're given a completely different circle. Okay. So A, we're finding the equation of the circle. Once we find the equation of that circle, we're going to find the x and y intercepts of that circle. After we do that, we have another circle being given to us. And here we're already given the equation. So we want to find the center and the radius of it. Okay. So first thing that we would like to do is, if we want the equation of a circle, is think about what do we need. We need the center and we need the radius. So the diameter passes through the center of the circle and it's twice the radius. So if we find this distance, then we can find what the radius is, right? Because it'll be half of this distance. And if we find this length, we can also use this to find the midpoint, which will give us our center. So we can find the distance between the 2 points and cut it in half to find the radius, which is R. We can also find the midpoint between these points to find the center of the circle. So that's what we'll do, because that's all that we need for the equation. So for R, we have 1/2 times the distance between this point and this point. Okay, so we just throw our pieces into our equation. And we're going to have the difference between -9/2 and 1/2. So again, it doesn't really actually matter what order we put them in, because we're going to end up squaring it and it's going to be positive anyways. Okay, so as long as we have these in here and we're subtracting them, we'll have the distance between them. Okay, same thing here. So 7/2 minus a -3/2 and then squaring it. So this is going to give us a -10/5, or sorry, -10/2, which is 5. Squaring 5 is 25. 7 minus 3 minus a -3 is also 10. Over 2 gives us 5. So this is 25 plus 25. Okay, we'll walk that down, right, which gives us 1/2 times the square root of 50. 50, obviously here, is 2 times 25. So square root of 25 is 5. So this is actually going to be a radius of 5/2 square root 2. Okay, so that's what's left over when we simplify this. So that's the radius. Okay, so I'm partway there for my equation. Next, I really just need the center. Again, the center is the midpoint, right? So r squared is 25/2. Because again, squaring this, that's going to be 50/4, right? 50/4. Take out the common 2 is 25/2. So r squared is 25/2. So my h and k, okay, which is the x and ym, I can use my formula. So 1/2 times the average of my x values, 1/2 times the average of my y values. Okay, so adding these together, -9 and a +1 is -8. 7 minus 3 is 4, because they already have their common denominators. So this is a 1/2 times a -4. And this is 1/2 times 2. So 1/2 times 2 is 1. 1/2 times 4 is 2. Okay, so -2 and 1 is my center. Therefore, the equation is x minus a -2. Minus is plus. Y minus my k, right? And then my r squared. So this is going to be the circle that has a diameter with endpoints at the given locations. Now part B was for us to find the x and y intercepts. Okay, we know that y-intercepts occur when the opposite value of interest, right? So if we're looking at y-intercepts, x is 0. So I take this equation and I make x equal 0. Okay, that's going to give me 4 plus y minus 1 squared equals 25/2. So 2 squared is 4. Y minus 1 squared is the y squared minus 2y plus 1. And then now I'm just going to solve this quadratic. Okay, I'm going to move everything over and zero out my equation. Okay, 4 plus 1 is 3. Minusing the 25/2 will give me the following, because again, 4 plus 1 is 5, right? So if I need to make that common denominator, or I could clear denominators and multiply everything by 2, that would be fine as well. Here I decided to keep it monic, however, so I'm just going to throw this all into the quadratic formula. I could have, again, multiplied everything by 2 and had 2y squared minus 4y minus 15 and thrown that into the quadratic formula. It really doesn't matter. Well, actually that's what I did, but I did it later. And then plug it into our formula and we can solve, right? So I know 4 times 15 is 60, or sorry, 4 times 15 is 60. So times 2, this is actually 120. So this is going to be 16 plus 120 with a 4 and a 4. So that'll be 1 plus something, okay? So 120 plus 16 is 136. Okay, I can pull out a factor of 4 here. So square root 4 is a factor of 136. So that comes out as 2. And so this is really 1 plus or minus 1/2 root 34, right? The 4 and the 4 is the 1. The 2/4 is the 1/2. And I'm left with square root 34. Okay. So those are my y-intercepts. Okay, so I cross the y-axis at 2 points. Okay, if I want to find my x-intercepts, it's the same thing. Y needs to be 0. So I substitute in 0 for y. And I'm going to expand this and expand this. I know that 1 squared is 1, so that doesn't do too much. This is x4 plus 4x plus 4. So very, very similar equation. Okay, this will be the 5. I'll subtract this, or I can multiply by 2. It doesn't matter when I do it. Okay. Here I decided to do it a little bit differently, and I completed the square. Okay. So I know to complete the square, I just need to add 4 to both sides. Just trying to show you guys there's different options available for doing these kinds of things, right? So this is a perfect square. This I can condense down into 25 minus 1, right? And then 1 is just 2 over 2, so this should be 23 over 2. Okay, I can square root both sides. I got x plus 2 plus or minus square root 23 over 2, and then I subtract the 2 over, and I can rationalize the denominator, which bumps this up times 2, right? So square root 2 on the bottom, so I got to multiply times square root 2 top and bottom to pull out a positive 1/2, and that turns this into square root 46. Okay, so these two values are my x-intercepts. Okay, part C, we want to find the equation of a circle from this crazy looking thing we have here. Okay, so if you notice, our goal, right, is to put into the equation of a circle. The equation of a circle is x minus h squared plus y minus h squared plus r squared. So if you think about that, x minus h squared, that's a perfect square. Y minus k squared, that's a perfect square. So if I want to put this into the form of a circle, I'm going to group my x terms together, okay, and I'm going to group my y terms together and complete the square. Okay, so remember, when you complete the square, you add in a constant. So when I combine the constant from completing the square with my x's and with my y's to this negative 15, that'll give me another constant, my radius squared, right? And then I can put these into the form necessary for a circle. So here, what I'm going to do, so I'm sure you guys keep seeing this thing here. Apologies, I'll just describe it for a second. I'm using Adobe, and every time I load, this file is so large that it keeps having to kind of to load something to do a little bit of work. So that's just a little toolbar there. Hopefully that doesn't happen on future videos. Maybe it's just something for right now. Okay, but for our equation here, if you notice, I have 2, 2, 8, and 4. Ideally, I would like to have x minus h, right, and a y minus k on the inside. Those things don't have 2's in front of them, or 5's, or anything like that. So what I'm going to do is I'm going to divide everything by 2, which is nice because most of the things here are even, right? So divide everything by 2. That bumps everything down by a factor of 2. So this goes from 8 to 4, from 4 to 2, and then here's half of my 15. I'm going to group my x terms together, group my y terms together, okay? X squared plus 4x, y squared minus 2y, and I'm going to complete the square. So this one is very easy, right? As long as you're familiar with factoring, you really don't need to look at the negative b over 2a squared term type of deal, right? To complete the square, it's going to be a 4. To complete this is going to be a positive 1, okay? So I will add 1 and I will add 4. If you want to do the math just to verify that, but we should be quite familiar with these perfect squares because they come up fairly often, right? So I'm adding plus 4 and plus 1 to both sides, okay? Plus 4 and plus 1. So I can combine these to be a single constant. And then here, this is a perfect square, and this here is a perfect square, okay? Now my numbers were not nice like they are here. I would have to figure out, you know, what constant to add in, that a naught prime term, right? The negative b over 2a squared. So here, this is just x plus 2 squared. This is just y minus 1 squared, okay? And this combines to 25 over 2. Now, this should be familiar to you because this is the same circle that we've been working with the whole time, okay? So now let's talk about symmetry, right? So we have symmetry about different axes. Okay, the first one is symmetry of our graph about the y-axis. Again, the y-axis is the up and down axis. So a graph is symmetric about the y-axis if for every point on the graph, xy, okay, the point negative xy is also on the graph, right? So you can think of this as flipping the graph about the y-axis and getting the exact same graph. So for instance, okay, I have this graph. If I were to spin it across the y-axis, I would end up with the exact same graph, okay? You have to do a little bit of mental visualization here, okay? This is the type of visualization that you'll have to do in calculus quite a bit, right? So it's a good little stepping stone point. But imagine if I took this point and I look at its opposite x value, go over here, it's at the exact same y value. So this point, okay, its distance from the y-axis is the exact same distance from the y-axis as this point. Maybe this is a little bit easier to see, right? If I'm up 1 square and I go over 1 square, if I look on the other side, it is also over 1 square and up 1 square, right? It has identical points. The y values are the same, okay, but the negative x values, okay? So plus 1, up 1, I land on the graph. Backwards 1, up 1, I also land on the graph. So is this symmetric about the y-axis? Again, if I were able to spin this around one time, I get the exact same graph, okay? Symmetry about the x-axis is the same thing, except when I spin it, I'm not spinning it around the y-axis, I'm spinning it across the x-axis, okay? And so what this means is that for every single point that I have on my graph that's xy, the point x negative y is also on the graph, okay? So again, we can think about this as flipping across the x-axis. So same thing here. This point, right, if this was just one of my, if this part didn't exist and this was my only part of the graph, and then I flipped it across this axis, I would get this line, okay? And that's why there is the symmetry. Every point here, right, has the same distance of x across, but this point and this point have opposite y values. Instead of going up, this one I had to go down, but I go down the same amount that I had to go up on this one, okay? The next is symmetry about the origin, or about the center, okay? So graph is symmetric about the origin if for every point x, y, the point negative x, negative y is also on the graph, okay? So you can think about this as rotating your graph 180 degrees, okay, and getting the same graph, or as flipping over the x-axis and then flipping over the y-axis, or over the y-axis and then the x-axis. It doesn't matter, but basically flipping it about both axes and you'll get the exact same graph back, okay? So look at this one. If I flip this first across the x-axis, I'll get that picture, okay? And if I take this picture after I flipped it and I flip it across this axis, I come back to my original, okay? So let's look at an example. I want to determine the symmetry of the equation y equals x cubed plus 1. Right? So for the y-axis, I need that the y values are the same when I change the signs of my x's, right? So wherever I see x, I'm going to replace that with negative x, and hopefully I come out with the same equation. If I do, right, if all my y's are the same, then I have symmetry across the y-axis. So here, negative x cubed, when I simplify that, negative x times negative x times negative x, I get a negative x cubed plus 1. That is not the same thing that I started with, okay? It's not the same thing I started with. Therefore, there is no symmetry across the y-axis, okay? For the x-axis, remember, I need to plug in opposite values of y. So if I plug in negative y everywhere and come out with the same thing, I have symmetry across the x-axis. So here I'm going to change the value of negative y, okay, or value of y. Having y negative really means that I'm really interested in y, right? So what I can do is I can multiply everything times negative. So a negative y means that the equality on the other side is also negative, right? And that is not the same thing that I started with, okay? So there's no symmetry across the x-axis. So the next one I have to check is the origin. Okay, so remember, for the origin, I'm going to change the sign of everything. I'm going to plug in a negative x and also change the sign of the y and work it down. Okay, so when I do this, changing the y, okay, so first of all, negative x cubed plus 1 gives me this negative x cubed plus 1. I know that already because I've done that. Okay, the negative y means I change the sign on all of those things, which is going to give me x cubed minus 1, which again is not the same thing that I started with. So the graph of y equals x cubed plus 1 does not have symmetry across the y-axis, does not have symmetry across the x-axis, and does not have symmetry across the origin. Okay, therefore it is not symmetric at all with regards to the axes. Okay, so it's possible that we do not have symmetry in our graph. So that's the fourth option. Right? So that's our video. I hope you liked it. I will see you guys on the next one.